So let's talk about graphene. You've probably heard of it, right? The so-called miracle material that was going to change, well, pretty much everything. But years after the initial excitement, a big question is still hanging in the air. Where is it? That's what we're going to dig into. We're going to separate the incredible hype from the complex reality. And what you're going to find is that the real story, well, it isn't about one single material. It's about a whole family of them.
I mean, just think about that for a second. What if there was one material so strong, so conductive, so completely revolutionary that it could redefine entire industries, from electronics all the way to energy? That was the incredible promise of graphene. And man, did it ever capture the world's imagination.
Okay, so what is this stuff really? Put simply, graphene is just a single, flat layer of carbon atoms, all arranged in this perfect little honeycomb pattern. You're looking at the very first true two-dimensional material ever discovered. It's basically the fundamental building block of the graphite in your pencil. But when you get it down to just one single layer, its properties are just absolutely off the charts.
Which brings us to a material of superlatives, unpacking the hype, because that's where this all started. When scientists first managed to isolate this stuff, the numbers they were seeing in the lab, they were just staggering. First up, strength. Graphene has a Young's modulus of 1 terapascal. Now, what on earth does that mean? It means that pound for pound, this stuff is over 100 times stronger than the strongest steel we can make. It is, quite literally, the strongest material ever tested, period.
So it's ridiculously strong. What else you got? Well, how about heat? Its thermal conductivity is over 3,000 watts per meter Kelvin. In simple terms, it's an exceptional conductor of heat. Way, way better than copper or silver. So you can immediately see why people got excited, right? Think about pulling heat away from our ever-shrinking electronics.
And then there are its optical properties, which are just bizarrely cool. It's almost perfectly transparent, absorbing just a tiny 2.3% of the light that passes through it. So think about that. You have something that's super strong, super conductive, and you can see right through it. That combination alone opened up a whole world of possibilities for things like flexible displays and next-gen solar cells.
So yeah, you can see why it earned the nickname Miracle Material. I mean, you put all that together and you get this absolutely insane list of superpowers. It's stronger than steel, more conductive than copper, transparent, flexible, and it's completely impermeable. Not even the smallest gas atom can get through it. In the perfect conditions of a lab, graphene really did seem like the perfect material.
All right, now for the production puzzle, from a flake to a factory. Because here's the thing, there was a huge catch. How do you take that perfect, tiny flake that you made in a research lab and start producing it reliably, affordably, and on an industrial scale? This became the central challenge.
And this comparison just lays out the problem so clearly. On the one hand, you've got the pristine stuff made in a lab, sometimes literally by using sticky tape to peel layers off graphite. It's nearly flawless, a perfect single layer with all those mind-blowing properties. But then you have what we can actually mass produce. This stuff comes as tiny flakes floating in a liquid or as thin films, and is full of defects, impurities, and variations in the number of layers. And all that messiness just compromises those miracle properties.
And if you're talking about high-end electronics, there's another, even bigger hurdle, the band gap problem. Okay, think of a transistor as a light switch for electricity. It needs to turn on and off to create the ones and zeros of digital data. Well, graphene is such a phenomenal conductor that its switch is basically stuck in the on position all the time. Without a way to reliably turn it off, which is what scientists call a band gap, you just can't use it to replace silicon in our computer chips.
So this massive gap between the potential in the lab and the reality of the market, well, it's fueled this huge, passionate debate about graphene's commercial future. And it's a debate that's playing out right now.
On one side, you still have the optimists. You see comments like this all over the internet. It reflects that feeling that, with the next big breakthrough, we're right on the cusp of making that huge leap forward, especially in areas like semiconductors.
But then for every one of those comments, you see one like this from the skeptics. This person is hitting on that exact band gap problem we just talked about. They're basically saying, for a transistor, it's just terrible. You get all this leak current because you can't properly shut it off. From this very practical point of view, it's just not scalable for those kinds of applications.
And these viewpoints are rooted in some very real, very frustrating business hurdles. If you're a company thinking about using graphene, first off, the initial cost for the high-quality stuff is a huge barrier. But even beyond cost, there's a consistency problem.
There's no industry standard for what graphene even means, so the quality you buy can be all over the map. On top of that, you have to compete with established materials that are cheap and well understood, all while trying to navigate this maze of unclear health and safety rules. It's tough.
So, graphene in the wild. Where is it now? With all these challenges, you might be wondering if graphene has even made it out of the lab at all. And the answer is yes, absolutely. It's just maybe not in the revolutionary change the world overnight way we all expected. Instead, it's finding its place in more specialized, more practical applications.
What's happening is that it's really finding its footing in two very different kinds of markets. On one hand, you have high-value specialized uses, like in advanced batteries and energy storage, which require higher grades of the material. And then, on the complete other end of the spectrum, it's being used in bulk as a simple additive, where just a little bit of lower-grade graphene can make materials like concrete, asphalt, and plastics a whole lot stronger.
And this table here really shows that spectrum beautifully. At the low-cost end, you've got cheap graphene oxide flakes, which are perfect for adding mechanical strength to concrete. A step up from that, you have liquid exfoliated graphene that's good enough for conductive inks. Then you start getting into the higher quality films, made through a process called CVD, which you'd need for something like a flexible display. And at the absolute peak, for ultra-precise scientific instruments, you need the most pristine, expensive graphene possible. It's a whole range of materials.
So, the graphene roadmap, a realistic future, what does it actually hold? Well, researchers have laid out a much more down-to-earth roadmap now. It's not about a sudden revolution, but about a gradual, steady integration of graphene into our technology.
If you look at the timeline for electronics, you can really see this slow and steady progression. We've already seen prototypes for touchscreens and foldable displays. The hope is that by around 2025, graphene could become competitive for high-frequency transistors, the kind needed for next-gen communications. And the holy grail? Logic transistors? Well, that might be possible closer to 2030, but only if some pretty fundamental challenges get solved first.
And this right here brings us to the most important takeaway of all. The whole idea of a graphene revolution was never really going to be about one miracle material swooping in and replacing everything else. The reality is much more interesting. There isn't just one graphene. There's a whole family of graphene-based materials, a whole toolbox of options. And the real future is about learning how to pick the right tool for the right job.
So maybe we should stop asking, when is the graphene revolution going to arrive? A much better question is this. Since graphene is not one material, but a whole family of them, as we learn to make them all, which specific type, for which specific job, will be the one that truly defines our future?